let's talk about OpenMP. In case of pre-thread or threads, we have to assign the number of threads we are going to be using. But the OpenMP is much more smart. We don't have to tell it what number of threads it needs to use. It does it for us. So let's look onto the normal OpenMP and other different clauses and different part of it. Starting with very simple, including the libraries, creating a procedure named random vector, assigning the vectors and int. So the pragma OMP parallel helps you parallelize the code. So we're creating a thread and thread themselves are dividing this, like it has divided the data for ourselves. So we don't have to tell like this thread has this value and all, making the code much more smaller. So it automatically assigns what thread needs to assign the values to what vector index, and after that inside the main initialized a size of 100 million, and then the s random times, it tells us that each time when we compile a new data is being generated, a new value is given to whatever we wanted, and after that we are allocating the memory dynamically to each array. So basically array 3 would be the sum of vector 3 with dynamic array. Vector 3 would be the sum of vector 1 and vector 2. And then we have started this clock, and random vector has its size and the name of the vector. Same goes for the other vector, and then after that we are using the OpenMP for parallelizing our addition here. Just a for loop, no need to create a function, even though you can create a function, that won't make much more difference. Then auto stop, and how to get the duration stop and start, getting the time, bring the value. Let's run our code. Compiling that code, and after compiling, execute. One, two, three, four, five, six. I have just pthread as well. Let's compile that as well. So we get the clear picture who is winning and who isn't. As you can see, pthread clearly won this just because the array size, the vector size wasn't that big of a deal for this. And in case we were using OpenMP, basically uses the most number of chunks, and the other thing that it does, it mostly uses all the threads most of the time, so that's why the overhead and all. Then whereas in case of pthread, I have just used the number of threads to be 4, so the overhead is much more smaller. If I increase the number of threads, the overhead ultimately would be much more. Then looking at different kinds of OpenMP, there's this called reduction clause. So The above part remains the same. The only difference is when it comes to the addition. So in case of using the reduction clause, it happens when you wanted to actually combine the result from all the threads. Like it could be done using the addition. So all those threads got the value and then added all those values together. So reduction is the one that deals with it. Let's run this as well. So reduction has taken much more slower time in case of the P thread. So OpenMP is definitely winning this case now. Now moving on to the atomic. So let's talk about the atomic one. Atomic one is like at that particular instance, only that thread could do the changes in that particular variable. So here everything remains same, but the only difference here is like we are using the pragma OMP atomic, which tells us like at that particular instance of time, only one thread has the access to this total, and after that, the other threads can take turns. So it has, I compiled the code and it has a time of this much more faster. Let's go to the other one. So I have this. We have discussed reduction. We have discussed atomic. Let's go with the critical. Now, above part remains similar as it is. Now, critical means we are dealing with the critical section. So here, in case of using the global variable, we just use a local variable and iterate the value into the global variable. That's what critical section does. So this information would be dealt by each thread individually, and they would be adding individually to that. No two threads could add inside this at once. So thread one takes the adds inside the total. Then after that, when it has done its job, thread two does that. So that's why here a local variable and global variable are separated. Let's compile this as well. A little bit overhead because the other one exists this thing. Let's move on to our scheduling.cpp. Now, there are different types of scheduling. I have done guided, and guided means like otherwise it has given the chunk size. It decides the chunk size by itself. So the chunk size could be much more bigger, but I when I say the scheduling is guided, it reduces the chunk size. So that's what it does. There are dynamic, there are static. All those have there are runtime, have their own merits and demerits. Let's compile this. So as you can see, if the chunk size is much more smaller, again the overhead plays a big role in it. Now the last one that we have is default.cpp. Here, all these things are shared. So there could be a problem in it. So, but it does the work smartly. Default, none shared. You can make it shared. You can assign it like I don't want to share anything between them. So let's compile this. But it is still faster than the schedule. So thanks for watching the video.